I want to talk about the depth versus time model. Now, this is one of my favorite models in the world because it's so profound with so many implications, starting with through calculus and then through calculus and even through differential equations. We can use this model to gain a lot of insight into both mathematical procedures and the way the real world behaves. Now, got a cylinder here, and there's a tube down here at the bottom. And I'm gonna fill this with water and hope it balances when I put it. Okay, now it doesn't balance, it's going to fall. But if it does balance, you're going to see the level of water decreasing through these various marks. And of course, we know what the depth is at each of these marks. So we're going to be able to, if we take a timer, figure out what the depth is as a function of time. So let's just see if this is going to work. There we go. Look at that. Okay. It turns out that the path that this water follows is a quadratic function. And it turns out that the depth is a quadratic function of time. I get water all over the floor here and they can be more careful. And of course, the shape of this parabola keeps changing because as the depth changes, there's less and less water above the hole, meaning there's going to be less and less pressure forcing water out of the cylinder. Now, I'm not sure how well the video is going to show the level of the water. And the probably see the marks pretty clearly. And hopefully you can see this parabola, which is pretty much deteriorated to drip. Okay, and water still dripping out. If there, it stopped dripping. Okay, now you can take a timer, and if you're able to see the water level, and I don't know for sure how well that's going to come through because I just spontaneously decided to do this model. I can locate other videos. I've got videos that show it very clearly. Well, anyhow, my point is that there are two quadratic functions here. There are two parabolas involved. Okay, so one of the parabolas looks like this. Let's let y equal the depth. And let's say centimeters. And we're going to use t instead of x. Time, let's say, in seconds. Then at the t equals 0 point, we got this depth, here's some depth. And then the graph comes down like a parabola until it hits the t-axis where the water level stops changing. And of course, the parabola continues on like this. It's still too flat over here. Oh, that's down here. Okay, now this part doesn't matter. We say this part's not in the domain of the thing that we're observing because once the water is down here, it doesn't rise back up, even though that's part of this quadratic function. It's not relevant to the real world. So there's a parabola. And of course, to get that parabola, we just take our toolkit parabola and we stretch it this way or stretch it this way, a little bit of both maybe, to make it fit the information we have. If I know how long it took and what the original height was, that's all I need to make my parabola. So if I've got this point, which is easy to observe, and this point, which is easy to observe, I can fit the parabola and I can predict what the depth should have been at any time between here and here. And if I've got accurate information, my predictions are going to be very good, especially if I do it algebraically as opposed to sketching. But if I do a good sketch, my predictions are going to be pretty doggone good. So there we have that. Also, you have this path. Then I can do it like this. Okay. For any given time, the path of the water stream. Okay. So this would be like y equals height of the water stream. And arbitrarily, we'll say the height is 0 here and it goes negative. And t, or x, x equals a little bit of a long description, say the horizontal position along the stream. Okay, so this is an actual picture of the stream. Okay, this is also a quadratic function. Now to get this one, you would take your parabola, parabola. You would flip it upside down. You have to find, oh boy, got one on the chalk tray. Okay. We got this. We flip the thing upside down like so. Then we stretch this out, stretch it this way. We do something, you know, either stretch it in this direction or stretch it in this direction to obtain the actual path of the stream. Now we do that analytically, but we can also see how it works geometrically. And we want to see this geometric process. Now we haven't described this, we haven't done a detailed example of it, so you don't necessarily know where we're headed with this, but that's an introduction to the depth versus climb model. And if you pause the video, you can measure the positions along this path of the stream, okay, positions along the stream at a given instant. And you can actually take a well-constructed graph here, flip it upside down, and use this part to model the position of the stream. Again, do that algebraically as well. It takes a little more doing. It's pretty easy to understand, though, what we do with the toolkit function to obtain our model. And once we understand that, then it's just a matter of being able to do the algebra.